Okay, so what we just did was we reviewed hypothesis testing, we reviewed p-value, and you notice that in all the examples we did with hypothesis testing, the claim that we talked about, if we converted it to mathematical notation, dealt with a proportion of success. So in this example, the proportion of success was the proportion of people in the world that recognized the grant. In all the other examples we did, if you noticed, we happen to use the same type of measurement, which is a proportion of success, over and over. So it turns out that in hypothesis testing, we can deal with different measurements as well. It doesn't have to be just a proportion of success. Just like back in chapter 7, when we talked about confidence intervals, when we were trying to estimate some number about the population, that number could be a proportion of success, or it could be a mean, or it could be a measured variation like a standard deviation. It doesn't have to be just this specific measurement or a proportion of success. So now we're going to talk about hypothesis testing extended to different measurements as well, like population means. So let's review that. Let's talk about it. So it turns out that even if now we talk about different concepts like extending hypothesis testing to these different measurements, it turns out that the framework that we used to talk about hypothesis testing specifically for P, the proportion of success, will be the exact same framework. So if you understand this, then extending it onto these other varieties will be very straightforward. And that's why we spent so much time on hypothesis testing just for this situation of P. But now we're going to extend it to different measurements. And it turns out that the framework, the general steps are exactly the same. First step, we're going to identify HO and H1. Second step, we're going to assume that HO is true. Next step, we're going to visualize the distribution. Identify the size of the tails by looking at whether it's a one-tail or two-tail test. And then the step after that is to decide whether the observation is in the body or the tail, so that we can reach the proper conclusion. Now, previously, the way that we decided whether the observation was in the body or the tail was that we compared the critical statistic where the tail started to the test statistic, which is came from a formula. So now when we talk about a different measurement involved in hypothesis testing, the way that we find Z critical might be from a different table, and the way that we calculate Z test might be from a different formula, but that'll be the only difference. Once we get those two measurements, we're going to use those two to decide whether the observation is in the body or the tail. And once we decide that, then our conclusions will be found the same way. If it's in the tail, then reject HO, accept H1. If it's in the body, then fail to reject HO, fail to accept H1. So the only difference will be in finding the critical statistic, which may be from a different table, and calculating Z-tests, which may be from a different formula. So now let's talk about an example where we use a different measurement in our hypothesis tests. So let's say that, remember all hypothesis tests have some claim or some idea that you have about the whole population. And let's say that in this example, let's say that you're taking a vacation, you're traveling, and let's say that you're interacting with the locals, and based on the limited interaction you have with these locals, you happen to notice that maybe the locals don't seem as smart as the people you're used to dealing with, which is the people in your home country. So in order to quantify that, let's say that we try to quantify smartness with an IQ test. And so let's say that you happen to know what the average IQ of your home country is. And because you're claiming that the people of this country aren't as smart, then we're going to say that the average IQ of the people in this new country is less than the average IQ in your home country, which is 100. So your claim then is that the mean IQ of country B is, let's say, lower than the mean IQ of your home country, which is 100. And so this is a claim or an idea that we have regarding the population, which in this case is country B. And then we're going to use an observation to try to test that claim. So let's say that in the observation you have a sample size of, let's say, 50. And let's say that in your sample of 50, you take these 50 people, give them all an IQ test, and then punch those 50 IQ scores in your calculator. Your calculator will give you a sample mean and a sample standard deviation for these 50 people. So let's say that the sample mean is 97. Let's say the sample standard deviation is 13. So based on this observation, you want to be able to formulate a correct conclusion for this whole population. And you want to be able to address this claim for the population. So we're going to use hypothesis testing. So now we're going to go through the same steps, step by step, and then that one part that is different, where we're comparing test statistic to critical statistic, we'll address that. But so far, the general framework will be the same. So we're going to identify HO and H1 by starting with a claim and then generating the second statement, the counterclaim. So what would the counterclaim be in this case? Yeah, so we're going to keep the number the same, and we're going to change just the direction of the inequalities. So that'll be the mean IQ of country B is less than or equal to 100. That'll be the counterclaim. Or greater than or equal to 100. That'll be the counterclaim. So now we're going to convert each of these statements into mathematical language, just like we did before. And so for the top one, it'll be, we're going to use this new symbol now. And you notice before we used the symbol of P, now we're using the symbol of mu, which stands for population mean. So here, this population mean, or the population mean IQ, is less than 100. And on the bottom one, the population mean is greater than or equal to 100. So, of these two statements, which one is null hypothesis? Yeah, the bottom one because it contains equality, just like before. And the other one will automatically be H1. And again, the null hypothesis is, strictly speaking, it's just the equal sign. So we're going to strip away everything in the original statement except for inequality. except for equality, and that'll be mean equals 100. So this will be the null hypothesis. And then the entire original statement, the other statement, will be the alternative hypothesis. Okay, so that was step one, just like before. Next step is to assume HO is true, but now HO will be that the true mean is equal to 100. And then, just like before, we're going to visualize the underlying assumption. So the reason we've been using a bell curve over and over so far is because the variable we're looking at is a number of successes out of another number of numbers, out of another number of trials. And we know that if that's our variable, then the probability of getting each answer of that variable ends up being a binomial probability distribution. That's why we ended up getting a binomial probability distribution and fitting that with a bell curve. And that's why we've been using the z-score table, because essentially we had a bell curve. But now, in this example, we're going to look at this distribution. And our variable here represents a sample mean. But you notice that everything observed, we don't know sigma, the population standard deviation. So if we are looking at a variable where we're trying to find the distribution of a sample mean when sigma is unknown, do you guys remember what the shape of that distribution is supposed to be? A t-distribution, excellent. So this is a t-distribution. So that's why this distribution now will be a t-distribution. And moving forward, when we're trying to find any critical values, like where the tail starts, then we're going to use this new table, this t-distribution table. We're no longer going to use the z-score table. But everything else is similar in that this distribution is going to have a certain area for the body and the tail. So let's say that our confidence level, which is given, is 95%. And again, that means the area of the body of this distribution will coincide with this confidence level of 95%. So the area of the body will be the same as the confidence level. And then everything left over, which is alpha, is 5%. So that alpha, or 5%, will be the area shared across all the tails. So in this case, do we have a one-tail test or a two-tail test? One. Yeah, very good. So always look at H1, and same as before, look at the number of inequalities. So this is only one inequality, so this is a one-tail test. Had this been mu is less than 100 or mu is greater than 100, that would have been a two-tail test. But this is a one-tail test. And is it a left tail or right tail? Yeah, left, because the variable is less than the numbers, so less is left on the number line. So this is a left tail test. So that means that you can draw just this one tail that's on the left side of the distribution. And all the tails should add up to alpha, which is 5%. There's only one tail here, so that one tail has the full 5%. So the area of the tails is alpha, and the area of the body is the confidence level of 95%. So that'll be here. Okay, so where this left tail starts, that's the critical statistic that'll come from a table. So in this case, because the distribution, the t-distribution, this, where the tail starts, will have a t-critical. So let's go ahead and try to find t-critical here. So remember the way the t-score chart is laid out. Go ahead and try to look this up on the t-score chart. The way it's laid out is the first column is degrees of freedom, which is n minus 1. So in this case, n is 50, so n minus 1 is 49, or find the closest one to 49. And then we're going to scroll over. If you look at the first two rows, one row says area and one tail, and the second row says area and two tails. So in this case, because we have a one-tail test, we're going to go to area and one tail of 5%. So go to that column and intersect it with the appropriate degrees of freedom. Yeah.
1.676.
1.676. Rest of you guys getting that?
Yeah.
Okay, good. All right, so that's our critical statistic, or where the tail actually starts. And that's found from, again, a table. It just happens to be a different table from the previous examples. So that's the critical statistic, which comes from a table. And then now we want to incorporate the actual observation in there. So the actual observation is that our sample mean is 97 that we actually observed. But this is going to have its own test statistic, and that's going to come from a formula. So recall all the test statistics, like z-test, came from a formula. So it turns out that the test statistic in this case will come from this formula. So t-test is equal to x bar minus the mean all over s over the square root of n. So let's go ahead and find t-test by just plugging in those numbers. Yeah.
That'd be negative 1.632.
Okay, rest of you guys got that. So x bar is going to be 97. The true mean IQ for this entire country B, we don't know what that is, but we're assuming that HO is true. So we're assuming that the true mean is 100 based on the null hypothesis. And then divide by S, which is the 13, divided by the square root of 50. So if you punch that in, we should be getting negative 1.632. So that's our t-test, that's our test statistic. So first of all, the t-critical that we just found, because of the way this table is laid out, it says for area and one tail, it gives you the t-score. But because the t distribution is symmetric, if it had been two tails, then it would have been the same t-score. One would just be negative, one would just be positive. But any t-score that is on the left side of the distribution will be negative, just like with the z-scores. So even though the table gives you this one t-score that's positive, it's because it doesn't know whether you're talking about a left tail or a right tail. But if we happen to have a left tail, then we should make it negative. So this t-score that we get from the table should be negative. So if the left tail starts at negative 1.676 and everything to the left of that is in the left tail, then our t-score of negative 1.632, is that in the body or the tail of the distribution? Okay, so it's really close, right? So this is negative 1.632, which is not as negative as this t critical, so it's going to be just to the right. So it's going to be here. So let's say it's here in the body of the distribution. So that'll have a test statistic whose value is negative 1.632. So that's just a little bit to the right of negative 1.676. So therefore, in this example, it's in the body of the distribution. So if our observation is in the body of the distribution, then now we're ready to go to step 3 here and answer this question. If the observation is in the body of the distribution, then that means that the observation is consistent with the idea that HO is true. You only have one observation so far regarding HO being true, so can you conclude that HO is true for all observations?
No.
Just because it was true for this one, exactly. So you cannot accept HO being true, so the best we can do is not discard the idea that HO is true, so do not reject HO. So again, do not reject HO doesn't mean that you can never reject HO in the future. Maybe later on in the future, if you have more evidence, you're able to reject HO. So another way of saying that is that there's not enough evidence now to be able to reject HO. And so, same thing with H1. We do not accept H1. So based on this evidence, don't just immediately accept H1, is what that's saying. And then, again, we always want to bring it back to the original claim. So the claim in this example is HO or H1. Yeah, it's H1, based on how we labeled it in step 1. So because we said to not accept H1, and the claim is H1, we're going to not accept the claim. So we don't have enough evidence yet to accept the claim. And again, remember, do not accept the claim doesn't mean reject the claim, but you can think of it intuitively as leaning towards rejecting the claim. So what this means is that we're not going to accept the claim, which doesn't mean we're going to reject the claim, but we're going to lean towards rejecting the claim. So we're going to lean towards rejecting this claim that the average IQ of this country, country B, is less than 100. Any questions? Okay, so you notice that this is the only difference. So we have this claim with this new measurement that involves a population mean as opposed to P, a population proportion of success. So this is a different measurement that's involved in this claim. And the only difference is that the underlying distribution is now a t-distribution versus a bell curve. And so to find t-critical, you're going to go to the t-score table versus the z-score table. And to find t-test, instead of using the z-test formula that we talked about before, we now use a t-test formula. That's this different formula. And so those two measurements are different. But once we calculate those two, the general framework is the same. And we can conclude whether the observation is in the body or the tail. And whether it's in the body or the tail, the conclusions that we make are exactly the same as before. Yeah.
For the P, will we still have a p-value, or would it be like p-value or something like that?
Okay, so very good question. So in terms of the p-value, we would find it in the same way, which is the exact same steps that we talked about before, which is relative to this observation, find the area in the same direction as the nearest tail. So the nearest tail here is the left tail. So relative to this observation, in this example, we want to find a left area. So that means we wanna find this left area here. But let's go ahead and, try to use the T-score table to find this area. So basically, all the areas are basically in the first two rows, and then we wanna find the T-score that is 1.676. So based on 49 degrees of freedom, find the closest T-score to 1.676, and go ahead and try to identify what the area should be. So again, we're trying to find a left area here relative to our T critical. Relative to our T test. Oh, sorry, our T test is 1.632, not the T critical. So we're looking for 1.632, and it's negative. But the chart is only gonna have positive T-scores. So ours is negative, but just keep that in mind. All we're trying to do is find the tail associated with it. So we're looking for 1.632. So you notice you might not be able to find this score exactly. You're gonna have to just find the closest one, yeah.
The closest that can see is 1.645.
Yeah, exactly. So the closest you'll see is 1.645.
I found 1.638.
Are you using the Z-score table or Z-score table? So make sure you're using the T-score table.
Yeah, 1.63.
Where did you find it?
Top right there, bro.
Oh, shit.
So 1.638, and if it had been 1.638, then what area of the tail is that associated with? 0.1?
Mm-hmm.
Okay, good. So here with 0.1, but you notice that, so the best conclusion you can make from the table is it's around 0.1. So this left area ends up being 0.1. And then the next step to finding the p-value is to take this area and multiply by the number of tails. So that's still the same, but this is a one-tail test, so then this would be this times 1, which is just 0.1. So the p-value would be approximately 0.1. But you notice that it's a rough approximation because this t-score table, the areas are laid out very far away. So you might have 0.1, you might have another one that is 0.05, you might have the next area as 0.01. So these areas are laid out very far apart from each other. So the approximation is not very good. And so the best we can do to finding p-value using the table is only rough approximations. So because of that, on a test, I'm not gonna ask you to find p-value using the t-score table. But on the homework, it might ask you to use technology. And the way that you do that would be to find the calculator associated with the table that you're trying to use and you want a more exact value for. So for this case, if the homework asks you to use technology, just Google T-score calculator, and you can use any of the free links, and the calculator will prompt you for the same values that you're trying to use when you use the table itself. But the calculator will just give you more exact answer than you would by using the table. Any questions? So long story short, the way that you find p-value when the hypothesis test involves the population mean is the same exact steps that you would use to find a p-value with z-scores. The only difference is that when you use the table, the t-score table is spaced very far apart in terms of the areas. So you're not gonna get an exact answer. In fact, you're gonna get an answer that's very approximate. And so because of that, on a test, I'm not gonna ask you to find p-value for this case of using the t-score table. Only in the case of using the z-score table will I ask you to find p-values. But on the homework, it might ask you to use technology to find p-value in this case. So in that case, just Google T-score calculator, and you'll be prompted for the same things. So for t-test, just enter in the calculator, this number, and the calculator will spit out an area that is much more exact. And you can use that area to calculate the p-value. So in this case, you would take that area and you would multiply by the number of tails, so that would be multiplied by 1, and that would be the p-value.
For the t-graph, do you have to still use the significant figures like 40, 49, or do you just pick any number that is as close to the t-test?
Yeah, so in terms of the degrees of freedom, just pick the closest one to n minus 1. So in this case, n minus 1 should be 49, but pick the closest one to the table. If 49 is not there, then use 50.
But in the practice, we picked out 1.638, and that was with 2 degrees of freedom. Does that matter?
Yeah, that's why, using the t-score table, we're not gonna get a very good approximation for the p-value, and that's why I'm not gonna ask you to find the p-value using the t-score table, on exams. But that's why homework might ask you to use technology. And so, using technology, the calculator will prompt you for the sample size, in which case it'll internally calculate a much more exact answer.
Okay.
Okay, any questions, guys? And so, we don't have a lot of time left, but the next thing that we're gonna talk about, probably in the next class, is we're talking about claims that involve now a different measurement still. So instead of a population mean or a P, a population proportional success, we'll talk about hypothesis test where the claim involves a measure of variation, like standard deviation or variance. So that will be for next time.